In this video, we're going to look at the effect of changing concentration on an equilibrium position through the lens of Le Chatelier's principle. So to start, we're going to talk about the relationship between the rate of a reaction and the concentration. So as a reminder, at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And so it's important to understand rates of reactions so that we can understand how equilibrium will shift when they're affected. So we're going to consider the very simple reaction of this pink atom reacting and forming this blue atom. And we have two scenarios. So these boxes represent a closed vessel. So our atoms are contained within that vessel. On the left, we have 3 pink and 3 blue. And on the right, we have 6 pink and 6 blue. So we've doubled the concentration going from box 1 to box 2. The rate of a reaction is related to concentration because of the number of collisions that can occur between atoms. So the rate of reaction is directly proportional to the concentration. And the reason for this is if you have a higher concentration, you're going to have more collisions between atoms. If you have more collisions, you'll have a higher rate of reaction. So in our diagram on the left, we have 3 of each atom. This is going to have a relatively low rate of collision. In our diagram on the right, we have significantly more atoms present, and so there's going to be more frequent collisions leading to reactions. And so anytime we increase the concentration of a substance, we're going to increase its reaction rate that consumes that substance. So how do we actually change the concentration of something in a reaction? Well, we can either add something or we can remove it. And so we're going to start with how do we go about adding something to a reaction and what might that look like? So let's imagine the reaction, the Haber process, where we have nitrogen gas plus hydrogen gas forming ammonia. If we wanted to increase the concentration of nitrogen gas, we would simply inject some nitrogen gas into whatever flask our reaction is taking place in. If we wanted to increase the concentration of ammonia, we would again simply inject some ammonia into the flask that the reaction is taking place in. By injecting only the species we're interested in, we can alter the concentration of only one species in our reaction and alter the rate of the reaction consuming that species. If we want to remove a reactant or product, it's often a little bit more difficult. The reason is that our reactions take place as a mixture. And so removing one reactant or one product is often more challenging than simply just pulling it out of the reaction. This is often done through a side reaction, either a neutralization reaction or a precipitation reaction. So we'll look at both of those really quickly and talk about how these reactions can alter the concentration. So imagine we have an acid-base equilibrium. So we have acetic acid, CH3COOH, reacting with water to form acetate and hydronium ions. If we wanted to decrease the concentration of hydronium ions, we can't simply pull them out of solution. We must react them with something. And one way to accomplish this is to add a strong base, So to add something like hydroxide, and the hydroxide is going to remove the hydronium by forming water. And so through this side reaction, we're able to reduce the concentration of our hydronium ions. We can also do this through precipitation. So I'm just going to delete the last reaction that I wrote down, and we'll look at precipitation. So imagine that we have the reaction, the following equilibrium. So we have copper chloride. This is a complex in solution. So we have a 2- complex. It reacts with water to form copper copper aqueous complex and chloride ions. If we wanted to reduce the concentration of chloride ions, we could simply add silver nitrate, because the addition of silver ions will form a silver chloride precipitate, which will effectively reduce the concentration of chloride. So anytime you see the addition of something that's not directly in the reaction, think about removing a reactant or product and look for possible neutralization or precipitation reactions. We're going to look at what happens when we increase the concentration of a reactant. So we are going to look at the Haber process. So that is when we have nitrogen and hydrogen in equilibrium with ammonia. On the left, we have a system at equilibrium. You'll notice that the concentrations of all the species are not equal. They don't have to be at equilibrium. All that matters is that our forward reaction and our reverse reaction are occurring at the same rate, meaning for every molecule of nitrogen that we consume, we produce another one by the reaction of ammonia. So we can introduce what we call a stress. So when we change something with the equilibrium system, it's called a stress. So if we add more nitrogen, we can see here now that we have lots more nitrogen present, same amount of hydrogen and ammonia. The reason that adding nitrogen is going to change our reaction rate is that now there are more molecules with which the hydrogen molecules can collide. And so this is going to increase the number of collisions that are occurring within this system, increasing the rate of the forward reaction. And so if we think about equilibrium where our forward reaction and our reverse reaction happen at the same rate, when we add our reactant in, all of a sudden we've greatly increased the rate of our forward reaction, but we haven't significantly changed the rate of our reverse reaction. And what that means is that we're going to produce more ammonia than we can use up. Because we are producing more than we can use, the concentration of ammonia is going to increase. On the flip side, we're using up more nitrogen and hydrogen than we can produce. Because of this, the concentration of nitrogen and the concentration of hydrogen will both decrease after our stress. This is called the shift. And because we are increasing the concentration of our products on the right side of the reaction and decreasing the concentrations of our reactants on the left side, this is often referred to as a shift right or a shift towards the products. So we've added more reactant, and the equilibrium is going to shift to remove the added reactant. So to remove the stress that was induced on this equilibrium system. We're going to look at what happens when we increase the concentration of a product this time. So the same reaction, the Haber process with nitrogen and hydrogen as our reactants and ammonia as our product. On the left, we have an equilibrium condition. On the right, we've added a stress. We've increased the concentration of NH3. And so we can see very clearly that there is a significant amount more NH3 present than there was at equilibrium. And because there's so much more NH3 present, it's going to collide much more frequently, increasing the rate of the reverse reaction. So before our stress, our equilibrium had equal rates of the forward and reverse reaction. After our stress, we had the same rate as before of our forward reaction, but now a significantly higher rate of the reverse reaction. And that's going to cause two things to happen. First, we're going to be producing our reactants, N2 and H2, at a higher rate than they can be consumed. When we do this, we're going to be increasing the concentration of those species. So we're going to increase the concentration of both of our reactants. On the flip side, we're going to be consuming NH3 at a much faster rate than it can be produced. This is going to decrease the concentration of NH3 in this reaction. So we're going to be increasing the concentration of our reactants on the left side of the reaction, decreasing the concentration of our reactants on the right, or their products on the right side of the reaction. This is going to be a shift left, or a shift towards our reactants. So we've added more product, and the equilibrium will shift to remove the added product. So to remove the stress that was induced. Now we're going to look at what happens when we decrease the concentration, and we're going to start by decreasing the concentration of a reactant. So the equilibrium system we have here is the complexation of iron thiocyanate. So our reactants are iron 3+, which is represented by the orange dots, thiocyanate, which is represented by the gray dots, and iron thiocyanate, which is a complex ion, which is represented by the red dots in solution. The stress we're going to impose on this equilibrium system is the addition of hydroxide ions. Hydroxide ions are not present in our original equilibrium. Hydroxide ions will precipitate out iron 3 hydroxide, and this is going to remove iron 3+ from the solution. When we remove something from the solution, we're going to decrease the rate of the reaction. So before, our equilibrium had equal rates of the forward and reverse reaction. Our reverse reaction rate will stay the same. However, our forward reaction rate will decrease because we have fewer reactants and therefore fewer collisions. The effect of this on the reaction is that iron thiocyanate will be consumed faster than it can be produced. This will lead to a decrease in the concentration of iron thiocyanate in solution. Conversely, iron will be produced faster than it can be consumed, as will thiocyanate. This is going to lead to an increase of both the concentration of iron and the concentration of thiocyanate. This will result in a shift left towards the reactants. So essentially, we're going to have a forward reaction that slows down while the reverse reaction stays at the same rate. Because we've removed a lot of reactant, the reaction will act to replace what we've removed. So our stress is removing the reactant, and the reaction will shift to replace or counteract that stress. We're going to look now at decreasing the concentration when we remove a product. So on the left, we have our equilibrium system. We have the copper chloride complex, represented by the green dots, water represented by pink, the copper hydrate, the copper water complex represented by blue, and chloride ions in purple. On the right, we're going to be introducing a stress, and this stress is the addition of silver nitrate. This is going to form a silver chloride precipitate and reduce the concentration or remove silver or chloride ions from solution. So before our stress, our equilibrium had equal rates of the forward and the reverse reaction. After our stress, our forward reaction rate doesn't change, but our reverse reaction rate gets small because we no longer have a lot of chloride ions around for the collisions to occur. So in our forward reaction, we are going to be consuming, and I'm just going to talk about the the copper chloride complex, just because water is going to be readily available. So we're consuming the copper chloride complex faster than it can be produced. That's going to lead to a decrease in the concentration of that complex, as well as water, as much as we can reduce the concentration of water. In our reverse reaction, we are going to be producing chloride faster than we can consume it. Similarly, we'll be producing the copper hydrate faster than we can consume it. This is going to lead to an increase in the concentration of both of our products. So our copper hydrate complex and our chloride complex, our chloride ions. This is going to lead to a shift right or towards our products. So if we remove a product, our equilibrium will shift to create more of that product and replace what we've removed.